Okay, we're starting, everybody. So light, when we talked, we made two quick videos on light. Everything all right over there?
Yeah.
Okay, good. I was just worried there. Okay. Now, we're looking at the nature of light, and we did all of this big intro about light and the universe and understanding it, and the accumulation of data in astronomy terms means understanding light. Now, what I found fascinating when I first started studying light as a kid was one of the theories of light was that when you opened your eyes illuminated whatever it was that you saw. So there were these invisible light rays that came out of your eyes and literally lit everything up. Now, it's a little weird. That's what they actually thought. They thought that your eyes illuminated everything. So yeah, I know. Like, so is your light interfering with my light? I guess they didn't get that far in their discussion, but okay, like close your eyes so I can see because there's too much glare. I'm sure they thought that glare had to do with too many people had their eyes open in one place. So I'm not sure how that all plays out, but what they began to understand was the concept of reflection. So let us reflect on reflection. Think of it this way. If you don't have reflecting light, you can't see anything. Right? Yeah, like for instance, stealth aircraft. We know about stealth aircraft from the first Gulf War, where the United States decided to make a parking lot out of Iraq and bombed them into the Stone Age. And they used stealth aircraft that couldn't be seen with conventional systems, such as whatever they were using for radar. We know radar. Radar is essentially some type of electromagnetic radiation that is reflected off aircraft and comes back and is received by the radar station, and you can make out what type of flying object it is. For instance, Mohammed, you're doing fine right back there? You're not bothering anyone? Excellent. Excellent. You're so wonderful. I appreciate that. For instance, radar was first experimented with early in World War II, where we had it, but the enemy didn't have it.
Wait, we by who's we?
The United States and Britain, the Allies had it,
Okay.
and the Axis did not have it.
Okay.
So, I know, right? Exactly. I know. You're right. Thank you. You're absolutely right. Those lines are constantly becoming less defined. Like, who was the enemy? It was us. You know, exactly. So, anyway, during the invasion of Pearl Harbor by the Japanese, for instance, they saw the planes, but they didn't really have that much experience with the radar. So radar is operated, and the concepts of radar is predicated on the concept of reflection. So you have light that hits an object, a mirror, for instance, and the light comes in at all different directions and is reflected. It's reflected. And when you see an object, you can see the object because of reflection. Now, we said that the sun and the stars and light-emitting bodies are emitting light and we're seeing the light. So why do we need to talk about reflected light in astronomy?
Does everything reflect light?
Right, comets are reflecting light, for instance, right? Unless it's passing through an atmosphere, and then you have friction, and you have this incandescence. Remember we talked about incandescence? Remember we talked about that? The conversion of heat to visible, right? Like a light bulb. That's why we kind of went into the concept of incandescence. Meteors, we see a meteor, we see that intense heat become so hot that it glows. Yes?
So you're saying the elements inside an object is what makes them that color?
We're not talking about color yet.
But like when the light shines on it and it's, well, to me it's all tied.
Yes, yes, and we're going to tie all of those loose ends together, trust me, and I'll address that in a moment, absolutely, absolutely. So hold on to that and don't let me forget it. In about 5 minutes, ask that question again, okay?
All right.
So I can see the moon because of reflected light. I can see Saturn and Jupiter's moons because of reflected light. And what's the light source for the illumination of those bodies in space? The sun, our sun, right? The sun. Okay, so reflected light is going to become very important. If the room is, if I turn off all of the light in a room, can I see anything in the room?
No.
No, I can't see anything. If there's absolutely positively not one speck of light, is there anything I can see? Absolutely not. No. Now there are instruments that I can use that will allow me to see at night. What kind of light do they use? How come they can see? Yeah. Infrared. Some use infrared light. And when people think of night goggles, they think of infrared, like in other words, heat. What kind of light is heat? Infrared. Okay. Now, what about goggles, night goggles that don't use infrared? What do they use? What do they use? What do they use? What do goggles, night goggles, what do they use?
Heat, like isn't it sometimes you can see the heat of like the body heat?
Right.
I don't know, maybe I'm just going all crazy with this one.
Well, a lot of it is infrared, Brianda. A lot of it's the infrared. But some of the goggles use simply light that's, it focuses whatever light is there. It can see little bits of light that the human eye can't pick up, and it magnifies it, it accumulates it, and it uses the little bits of light that are still there that the human eye can't possibly make out. So not every goggle uses infrared light. Some use leftover visible light and other forms of light. So you can use whatever the instruments are detecting. Aren't your eyes really like an instrument? Your eyes simply are instruments that use visible light, but you use infrared light as well, or light that's left over. I need somebody. Melissa, would you look up different types of night goggles and how what is it that they use in order to see? Okay, so why don't we look that up so we have a little bit more information on that. All right, we're going to talk first about we're going to look at electromagnetic radiation. We talked about it on the last film, but I want to tie some loose ends together. We have long wavelengths here, and then the wavelengths shorten, and they shorten, and then they become very short. Okay. Now, I want to talk a little bit about wave mechanics. What was the distance between two waves? What's that distance called? Remember? It's called what? It's called what? Remember this signal, that sign? It's called lambda. Okay?
Lambda?
Yeah.
Oh,
the Greek
yes,
letter,
correct.
lambda. And that means wavelength. Wavelength, or you could say one cycle. Okay? Wavelength is the correct name for it, but I'm going to throw in there cycle for a reason. Okay? In other words, I could have couldn't that be the wavelength too? Couldn't it be? Couldn't it? Yeah. Couldn't this be the wavelength going from here to there, just the same point of each wave, right? One wavelength. The distance from, traditionally what we say is the distance from one crest to the other. That distance is the wavelength, okay? But it could be simply one cycle of the wave, correct? All right, now. Then you have what? You have the speed of light. You have the speed of light, which is actually c, which is speed of light. My shoulder is just not working well today. You have the speed of light, we have wavelength. What are the unit labels for the speed of light? What do we use? Meters per second. What about wavelength?
Well, when I was going through the book, they use kilometers per second.
Okay, we use kilometers per second. That's right. Actually,
which one's like the most?
Kilometers per second. Kilometers per second. We'll use kilometers per second. And I'm going to tell you why. Okay. No, you know what? Let's use meters per second. I just had my brain just did something weird there. Did you notice that? Did it make a noise? You see, I always get confused with kilograms and grams and kilometers and meters, not in terms of what's distance and what's mass. But the kilogram is the SI unit for mass, not grams. Although chemistry, you would never know that, right? But in terms of length, people always want to say kilometer, but it's actually meter. That is the SI unit for distance. So meter is official. Meter is the official one for distance.
So you're saying
and kilogram is for mass. Well, you can use whatever you want. No. You can use whatever you want as long as you know what you're using, and that all of your calculations are consistent with what you're using. That's all. So you just got to make sure you know. You can use pounds for all I care. You know, you can use whatever you want, but you've got to make sure that if you're going to combine, like let's say you have mass and volume, and I say mass divided by volume is density, right? And we know that density, according to SI units, it would be kilograms over cubic meters. But in chemistry, you say what? You say grams per milliliter, right? Always, usually, grams per cubic centimeter. But in physics, you're going to say, kilograms per cubic meter, because in physics, we tend to use more standard units, the more SI units than in chemistry. But if you want to use pounds per square inch, that's not a problem, or pounds per cubic foot, as long as you know what you're using. Okay? Now, so what would the wavelength be? If this is meters per second, this would probably be, in terms of length, it would be probably what? Wavelength, and we just said the standard units of length are meters, so this would probably be meters. Now, there's another one. There's another one, and that's going to be frequency. In other words, if I have a point right here, and this light, this is going 3 times 10 to the 8th meters per second. Right? It's going that fast. How many of these wavelengths are going past us? Right? That's 1, 2, 3, 4, 5. Those are how many wavelengths, right, per second, right? So, in other words, you would say the frequency would be wavelength per 1 second. Would that make sense to you? Would that make sense to you? Yes or no?
Yes.
I mean, does that make sense, right?
Yes.
Yeah, I mean, that's what it is. But we don't say wavelength per second. That would be far too easy, wouldn't it? We don't say wavelength per second. I know, it's bizarre. But we don't say wavelength per second. We say this. I'm going to erase this. Move this up a little bit. What do we say instead? Anybody read the book? Take notes? What do we say instead? I want to spend a little time on just this little bit of information. We say what? We say, yeah! We say cycles per 1 second. We say cycles per 1 second. Instead of a wavelength, we call it a cycle. Remember I said it doesn't matter where you start in the wave as long as it's 1 cycle, right? Yes? But then that's too difficult for some people, so we don't even say that. We say simply, pick a number, we'll just 10. Let's say the frequency was 10 cycles per second. Is that okay? So 10 cycles per second. If you said that to me, I'd say, all right, you're right. But we don't say that. You know what we say instead? We say 10 per second. But then we say, no, we don't want to say that. Because doesn't that second have a known exponent of 1? Doesn't it? So pick a letter. Pick any letter. Pick a letter. M. Okay, M. How many M's are there? So we would have an exponent of what? 1. Right? Well, we don't put a 1 there, do we? We would only put like a 2, 3, right? Yeah. So there's a 1 there, right? Now remember this, 1 over a to the n equals a to the negative n. When I take, listen carefully, when I take the reciprocal of a base, blah, blah, bless you. When I take the you ready? This is really confusing, okay? When I take the reciprocal of a base, when I take the multiplicative inverse of a base, I take the additive inverse of the exponent. Weird or what? When I take the what's the multiplicative inverse?
Do you write down the example?
I am. I know. It's like your brain's starting to hurt. What does it mean, multiplicative inverse? What's another name for that? Starts with an R. I already said it. Reciprocal, yeah. What's the reciprocal of 5? 1 over 5. What's the reciprocal of x? 1 over x. Good. Okay, good. When you take the reciprocal of a base, you take the additive inverse of the exponent. What does that mean? What's an additive inverse? What's the additive inverse of positive 5? Negative 5. What's the additive inverse of negative 5? Positive 5. So I'm going to take the additive inverse of s, 1 over s to the 1. What's that going to equal? S to the negative 1, right? Right, isn't that right? Okay, so wouldn't this therefore, this is so bizarre, I know. I know. Does it seem like Mr. Darcy's making a big deal out of this? Well, he is, because students who are not used to physics wonder, where did all that come from? So instead of saying cycles per second, instead of saying wavelengths per second, you'd think cycles per second, right? Instead of saying cycles per second, we say per second, right? Instead of saying per second, we say s to the negative 1. Am I done? Nope. And this you've heard of. This you've heard of. Are you ready? Instead of saying s to the negative 1, you know what we say? Hertz. Have you ever been in a room? What kind of lighting is this? Fluorescent lighting. Have you ever been in a room where you get that hum with fluorescent lighting? It drives you out of your mind. It drives you crazy, right? You know what that hum is? That hum are their vibrations. It's like, it's sound, right? It's not light, it's sound, right? In other words, here's the sound. You ready? Here's the sound. This is 1 cycle per 1 second for sound. You ready? Right? Right? That hum is 60 cycles. 60 beats a second. That's a frequency. 60 hertz. So frequency in sound or light can be called hertz. Yes? Sound amplifiers, you know, things like that, you have hertz, right? Electronics, for light, you have hertz. Okay? So you can have s to the negative 1 or hertz. Clear? Look at section 3 and throw out some hertz for me. Throw out some frequency. What does it say the unit labels for frequency is? What does it say? What does it say the unit labels for frequency? Look at the bottom of page 536. What does it say in the bottom of 536? What does it say? Doesn't it say frequency in hertz? That's what hertz is. And what are some hertz?
12 hertz.
10 to the 12th. Okay. Right? 10 to the 12th. What about visible light? What's visible light? 10 to the 15th. Let's do this. Let's do this. Somebody look up Semyon and Sophia. Look up the frequency of red light. The frequency of red light. What do you got? The frequency of red light. You got it? You have it already? How do you have it? Oh, you were doing color?
Yeah, no, you gave me 3 primary colors.
All right. So what did you say it was? And I want these guys are going to verify. What do you got, Sam? What do you got?
4 times 1014 HC is red light.
4 times 10 to the 14th?
Yeah. 14.
No.
1014.
1014.
101.
I don't understand.
4 times 1014.
That's what they wrote.
You wrote that, or who wrote that? I think what they're trying to say is they're trying to say 4 times 10 to the 14th HZ is the abbreviation for hertz. I don't think they're saying 1014. Yeah, 1014. All right, we're going to go off camera just for a second. Let me see. Yeah, they mean 4 times 10 to the 14th. That's red light.
Oh, okay.
Yeah, what do you, did you guys look it up? What do you guys got? Yeah, that's what they mean. They just couldn't do, they didn't know how to do exponents. Yeah, it's kind of weird. Like HTML, they didn't know how to do an exponent. Sammy, did you get it? Same thing? Yeah. Okay, and what is violet light?
It is 8 times the 14.
Yeah.
8 times 10 to the 14th?
Yes.
Yes.
That's violet light?
Yes.
Okay, so very close, aren't they? Very close. Yes or no?
Yeah. And then all in between is the color of the rainbow?
Yeah,
Yes.
14.
So, exactly. So here's red. Red, orange, yellow, green, blue, indigo, violet. Right? So over here is 4 times 10 to the 14th hertz. And here is 8 times 10 to the 14th hertz. That's what our eyes see. Those are the limits of our sight. Did you know that we don't see red light very well? I mean, we see it, but not really well. I mean, we're told we're supposed to be able to see it because, you know, you make things red so you can notice it. It's a lot of hoo-ha.
Isn't this type of yellow almost like...
Yes, it's called chartreuse. That's right. Let's talk about that just for a second. We're kind of getting a little bit off track, but it's still consistent with what we're doing. Okay? So, can you see right here? Can you see that? Is it up there? On the video? The video. Sammy's looking in the back. I'm pointing. Okay, you're right, you're right. So let's say this is red, orange, yellow, green, blue, indigo, violet, right? It kind of goes like this. Right? And it's like right there. This color here is called, how do you spell chartreuse? I have no idea. Not only can't I pronounce French words, I can't spell them. You know how you spell car, the word car in French? M-I-L-L-E-R. I'm kidding. I'm kidding. I can't pronounce that. How do you spell chartreuse? Look up chartreuse.
C-H-A-R.
Wait a second. C-H-A-R-T-R-E-U-S. That's actually pretty reasonable. Anybody speak French in here? Sammy, do you speak French?
Yeah.
How do you say that word?
I like attempt to speak French.
Chartreuse. Chartreuse.
Speak French.
You speak French? How do you say that word? Chartreuse. It's one of the few words that actually looks like, the English do the same thing, right? D-A-R-B-Y, Darby, is actually pronounced Derby. No, Derby, no. D-E-R-B-Y, Derby is pronounced Darby, yeah. Anyway, that color, it's kind of like a lime, green, yellow, lime, green, right? You see rescue workers. Could you remove that sweater for me just for a moment? Okay. This color here, see that color? That horrid color? Sorry. That horrid, it's, yeah. People can see you coming. You gotta see it? Can I see it? How's that? Is that good?
Yeah.
Is that good?
Yeah.
That lime green, all right? So we know when Sammy is coming, okay? We can be blind as a bat. There's Samia, she wants some attention, okay? Right? Now, the reason, it's a very nice sweatshirt.
I actually got it as a present, so.
It is ugly as sin. No, I'm kidding. Rescue workers, I'll tell you a quick story. This goes out to Paul, my friend Paul, who's British. Shout out to Paul, buddy of mine in I used to be on. He's an EMT. I think he's in Pennsylvania somewhere.
He's the one that
He's an
tore my
EMT,
head.
emergency medical technician. But anyway, so he's organizing the new rescue vehicle, and he's helping design it. He's working with the company, and he wants to put a chartreuse stripe around the bottom of it. And everybody in the squad is like, no, we want hunter green, dark green, and it's going to be an ugly color. And he's like, and everybody's like going crazy. And I said, wait a second, this isn't. And he said, saying, this isn't about aesthetics. This is about safety. It's ugly for a reason. It's the dominant color from the sun. Our eyes, and you see rescue workers with the little vests on, the road workers here in Abu Dhabi. You see them with that color. You wonder, why don't they wear red or orange, right? Well, those are not as effective because our eyes evolved over literally thousands and thousands and thousands of years to notice that color. It's the dominant color from the sun. Matter of fact, the sky, we don't see violet light very well. The sky is actually violet, it's not blue. But we see cyan. It's purple, yeah, I know. The sky is violet, purple, I know. Next time somebody says the sky is blue, say, sorry. It is purple. Purple, violet. Yeah, it's in that family. Obviously, the sky has a variety of shades. Is there a lot of humidity? Is there sunshine? Is it winter? Is it, right?
Sometimes it has to be white here, like, right?
Yeah, it's so white, yeah, because of sand and humidity, it is anything but blue, yet there's not a cloud in the sky and there's not a lot of pollution. But out in the desert, it can be horrid looking, yes.
Is it true that there are colors that the human eye cannot see?
Yes, I guess. I'm not quite sure I follow you, but I'll say this about that. The question was, is it true that there are colors that the human eye cannot see? Well, red we see, but not very well. You see how there's not a lot there? This is the way the curve comes, the bell-shaped curve. Yes, this is not perfectly drawn. Even though I sometimes might be very creative, I have no skills for painting or anything. But violet, we see hardly any violet. You've got to really shove a lot of violet, pigment in there for us to even see it. Don't be confused between pigment and light. Different. So the lights, violet light. So are there colors that we don't see? Well, yeah, violet and red we don't see real well. There is a lot of light we don't see. Okay. For instance, and that's where I'm going to next. So here are the limits of the range, right? So give me a frequency for radio waves. Give me a frequency for radio waves. Here's radio waves here. That's on one end of the spectrum with very long waves. Give me a frequency. What is it? You have it on your computer? I'm having a hard time. It says radio waves. 10 to the 6th. Okay, good. All right, 10 to the 18th okay. So 10 to the 6th. So this is 10 to the 6th, right? Yes? Visible light, 10 to the 14th, right? And what's gamma rays? 10 to the 18th. So look at this range. Look at the range, right? Look at the range. So you go from millions through billions and trillions and whatever that is. That's like 100 trillion, right? It's a lot, right? And then you have 10,000, 100 trillions, right? So yeah, there's a lot we don't see. Are there other colors in there that? Well, yeah. You don't see bees a lot. So there's certain bees on a cloudy day, do you? Because they use ultraviolet rays to see. Okay, so it depends on the organism. Some organisms use, visible light. Some use ultraviolet light. That sort of thing. So it depends on the organism. So there's a lot of light that we can't see. Now,
Is there any way to see it? Like, with
Sure.
some kind of surgery or whatnot?
I'm not sure. I would doubt there's any kind of research on that unless somebody with very nefarious goals performed an operation so someone could see ultraviolet light. But that sounds like something out of Star Trek. But anyway, there's instrumentation that you can use that can see objects using other forms. Do we have the answer to that? Say that again. The types of instrumentation was that Melissa? Was that you and Mohammed? And what did you find out? The question is was there surgery that can be performed on an eye, whatever? It's instrumentation, isn't it? Really? So go ahead. What did you find, Melissa? There's 3 types of goggles. Okay. And what kind of light do they use? How do they work? In one sentence or less, each goggle. Passive night vision. What does that mean? They use what? Okay. Oh, night sky. They use smaller quantities of light to see. Okay, I got you. All right, passive night vision. Okay, go ahead. What else? Infrared light source. That's active night vision. And then what's the other one? Thermal imaging. Now, how is thermal imaging? We'll talk later, but the question is, how is thermal imaging different from infrared? That's an interesting question. Let's talk about that off camera, and I'll give you a little bit of a project to do. Okay, I want to quit here, but then I want to make another quick one to talk about the relationship between or among the frequency, the speed, and the wavelength. Is there a relationship? Is there a relationship, a mathematical relationship among the speed, the frequency, and the wavelength? Okay? We're off.